There are about 12 gallons of water in the average teenage moron, 5 trillion gallons of water in this really cool lake, and 370 million trillion gallons of water on our entire planet. Water is abundant on our little jewel of life in the middle of the universe, and it has become synonymous, almost inseparable from life. But why? Why is it water that our bodies use to keep us alive, that helps plants continue to grow, and keeps our entire planet as a whole stable? Those are really good questions, and hopefully I can help you understand the answers on today's video, Understanding Water. To understand why water helps sustain life in and around us, we're going to zoom in super small to see what makes an individual molecule of water unique. Then we can zoom out in increasingly large increments to see how the special properties of that molecule allow it to sustain life all around us. Let's get started. This is a water molecule, also well known as H2O. While I haven't drawn it to scale, in real life it would be about 0.3 of a nanometer wide. It would take about 6 billion of these molecules lined up to be as tall as I am. That's a little side project for those of you who are interested. Comment down below if you're able to figure out my height. Understanding what makes water so important begins with understanding the unique properties that it possesses. Each water molecule has 2 atoms of hydrogen and 1 atom of oxygen. These aren't rare or special atoms by any means. In fact, they're absurdly common. However, it's how the atoms are arranged and the ratio of hydrogen to oxygen that makes water special. Because the atoms are structured in this specific way, with the 2 hydrogens on one side and the oxygen on the other, it gives a water molecule a unique property, a small magnetic field that is called polarity. Because of the distribution of protons and electrons, the side with the hydrogen atoms is going to be slightly more positive, and the side with the oxygen atom is going to be slightly more negative. At its most basic level, it is this magnetic property that allows water to sustain life in the way that it does. This is because of 2 reasons. The first is that it allows water molecules to group closely together. It uses hydrogen bonds, the attraction between the more positive side of one molecule to the more negative end of another. This causes what we call cohesion, the ability of a large amount of molecules to stick together. The second thing that the small magnetic field allows water molecules to do is dissolve other objects, which I will explain later in this video. Those 2 properties are the most important when it comes to explaining how water can sustain life. Now, there are others which I will allude to in the rest of the video, but for now, those are the most important. Now that we understand how water itself is a unique molecule, let's zoom out a little bit and see how it helps one of the smallest things stay alive, a cell. This is a macrophage, a super important immune cell. But even more important for us, it contains the average amount of water for a cell, with about 70% of its total volume being water. That amounts to a whopping total of 1 quadrillionth of a gallon. Now, to us, that seems like basically nothing. But if it wasn't for that seemingly inconsiderable amount of water, this cell would be about as alive as a slab of concrete. But why does water hold the key to this cell's life? Well, while there are multiple reasons, one of the most important is that it uses water to help facilitate the transportation of nutrients, wastes, and products within a cell. Allow me to explain with a likely overused analogy. You can think of a cell like a factory. Like any factory, a cell has to take in raw materials, create goods, and send them out into the world. However, a cell also has to keep itself alive in the process. Both factories and cells need some sort of way to move stuff around inside of them. Factories use belts, forklifts, and oversized Roombas. I know, the oversized vacuum bots are more of an Amazon warehouse thing. Just let me have my moment. Cells, however, use something different. They use the properties of water to help move things around inside of the cell. As a material enters the cell, it's not like it's inside of a truck on top of a road. Instead, the material is completely surrounded by water molecules. Those molecules give support to the material on all sides and allow it to move through them to get to its destination. In this situation, water is called a medium of transport because it allows materials to go through it. We talked a little bit earlier about water's magnetic properties, and here is where it becomes super important. Those small magnetic forces from the hydrogen bonds are what allow water molecules to stick together. This gives any object that contains water, like a cell, a good amount of structure. Now, the hydrogen bonds aren't too strong, otherwise no material could travel through them. On the other hand, they're not so weak that the molecules would spread apart too far. Then, any object that contained water wouldn't have structure at all. The magnetic property of water molecules helps move things around in a cell in more ways than one, though. A different way is that it helps by dissolving large objects. This allows a bigger compound to be broken down into smaller pieces. And as anyone who's ever had to move literally anything knows, it's always easier to move a smaller object than a larger one. Water dissolves things for two main reasons. The first is that it is polar. This allows it to be attracted to other polar objects. This includes other water molecules, but also molecules such as salt and sugars. The second reason is that the bonds between water molecules are often stronger than the bonds between, say, salt molecules. This means that as the water is attracted to the salt, it's able to break it away from its main crystal, slowly breaking it down and dissolving it. Sound complicated? Yeah, it did to me too. So here's another way of thinking about it. I want you to imagine a game of tug of war with 5 people on each side. The rules of this game are going to be a little different though. There's going to be 2 variations. The first is that only the person in the front of the line can actually hold on to the rope itself. The rest of the players just need to try to hold on to each other the best they can. The second variation is that you're not trying to pull someone across a mark in the ground, you're trying to separate that leader from his friends. The players on the left decided to just hold on to each other with their hands. The players on the right decided to tie themselves to each other with a rope. Now, if you had to guess which leader is going to be separated from the pack first, if you said the group on the left, you'd be correct. Because they weren't connected to each other as tightly as the group on the right, their bond with one another was weaker, so it was easy to separate the leader from the rest of his friends. It's the exact same way with water molecules. Because the bond they have with each other is so strong, if attraction ever occurs between water and something like salt, it's the salt molecule that's ripped away from the rest of its friends and drawn toward the water, not the other way around. All right, so now we've looked at how a cell uses water to help move around things inside of it efficiently. This is because water has the perfect amount of cohesion, or the ability to stick to other water molecules. This gives it the ability to move or break things, which allows it to help get items where they need to go. So if that's how water helps support life inside of a cell, what about on a larger scale? What about as a person? Well, let's go find out. As a 160-pound male, I contain approximately 11 to 12 gallons of water, depending on the day. Now, that's a lot more water than what was in the cells we were talking about earlier. But considering that our bodies contain trillions and trillions of cells, it does make pretty good sense. At this level, water helping with transportation is still a vital process, helping get things from our intestines into our bloodstream and to reach our individual cells. However, the larger an organism gets, a new important concept emerges. That is thermoregulation. Now, that's basically just a fancy word for making sure your body stays at the temperature it wants to stay at. So, not dying when you step outside on a summer day in Louisiana or a winter day in Nebraska. Most people are familiar with the idea of sweating and how that helps cool you down. However, water plays a vital role in maintaining your temperature even before you start shivering or sweating. Let me explain why. When any object is hot, the only thing that means is that the molecules that make up that object are moving more quickly. More movement means more heat, and less movement means less heat. So if you want to change the temperature of something, the only thing you have to do is make the molecules move faster, right? Well, while that is part of the story, there is another step involved in changing the temperature of an object. Before you're able to make the molecules move more or less freely, you need to loosen or tighten the bonds that hold them together. Because water molecules have a pretty strong hydrogen bond that holds them together, if you wanted to do something like heat that water up, first energy would have to be expended to loosen the bonds that hold the molecules together. Then, once that has happened, energy can be used to move the molecules themselves. However, by that point, your body will have likely already detected the temperature change and started to deploy countermeasures to make sure that you don't die, basically. This is one of the many ways that water helps keep us as humans alive, by maintaining a steady internal temperature over a long period of time, thanks to water's stubbornness to temperature change because of its strong hydrogen bonds. Now that we've looked at how water keeps us as humans alive, why don't we zoom out to the biggest scale to see how water not only affects us as people, but maintains the health of the entire planet. On Earth, there are about 370 million trillion gallons of water, an amount so insane that it is hard to even comprehend or quantify. But it sounded fun, so I decided to do it anyways. If you took all the water in the world and put it into 5-gallon buckets like this, you would need about 74 quintillion buckets. If each bucket was 1.2 feet tall and you stacked them all on top of each other, it would create a tower about 17 quadrillion miles tall. You know another way you can measure that in? Light years. About 2,900 of them. So yeah, we have a lot of water. The ideas of transport and temperature regulation are just as important on the planetary level as they were to cells or humans. But here, there is something else that water takes a part in that keeps our planet alive and healthy. And that is the water cycle. I'm sure you've all heard about the water cycle at some point. Water in rivers, lakes, and oceans warms up, evaporates into the atmosphere, cools and condenses into clouds, and eventually comes back down to Earth in the form of rain, snow, hail, hurricanes, and various other wonderful displays of Mother Nature's power. I'm sure you're all thinking, yeah, I know, what's the point? Well, the reason the water cycle is even able to happen in the first place is because water has the unique ability to exist as a solid, liquid, and gas, all within Earth's normal range of temperatures. This ability is so unique, in fact, that water is basically the only chemical on Earth to be able to do so, period. This is because water has the perfect amount of cohesion, a common theme I hope you're catching on. The hydrogen bonds it has allow water to be a solid and a liquid at some of Earth's temperatures, while not being so tight that it prevents water from evaporating at others. Think about what that means for a second. If water had a higher boiling point, so it took more heat to make water evaporate, more of the Earth would be covered in ice, and less water would be able to evaporate into the atmosphere and eventually come back down as rain. This would lead to droughts and it would likely cause food shortages and a decrease in the total amount of farmable land. If it was the opposite of that, though, the planet would have a much different problem. There would be considerably less ice at the poles, which would cause an increase in the water level of the entire planet. This would likely lead to a massive decrease in the total amount of livable land area. Lakes and rivers would be considerably smaller. Aquatic life would die because of stress caused by rapid phase changes, and the climate would experience massive shifts due to large amounts of steam-like fog in the atmosphere. Fortunately for us, though, none of that is the case. Water truly hits the Goldilocks effect, inherently having the perfect amount of cohesion to exist in the right phase at the right temperature on Earth, allowing it to sustain all life as we know it. And that is mostly it for understanding why water is basically a miracle chemical. It all boils down to the fact that water is a polar molecule with slight magnetic poles. This allows it to form hydrogen bonds with other water molecules and have the perfect amount of cohesive force while doing so. This means that water can help transport and break down nutrients, maintain the temperature of organisms, and change phases at the right temperatures on planet Earth. I hope that you truly enjoyed this video. If you did, please hit the like button and subscribe to my channel. If you have any ideas at all for a topic you want me to cover, please let me know in the comments down below. I hope that I was able to help you increase your knowledge and appreciation of simple H2O on today's video of Understand It.